Hello and welcome to the 57th lecture in this series. Let me resume from where I had stopped last time. That was showing anti-commutativity of the wedge product operation. So I remarked that it's enough to show that for the basis that we have constructed, the same property holds. Well, again, let's use this the main lemma, which is about concatenation and wedge product. So this equals epsilon ij, while the right hand side is okay. Before I move on to the right hand side, let me just, this is the same as sine tau multiplied by epsilon ji, where after all the ij just consists of concatenating these two indices. Now the thing is that and ji as sets without any order, ij and ji are the same sets. So we can use a permutation to go from ij to ji, that's the permutation tau, and we know that when the index set is changed, that the epsilon changes in this fashion. This is one of the lemmas that we had proved earlier, where tau is the permutation taking ij to ji. So this is what we get, and finally, so therefore epsilon I wedge epsilon j equals sine tau epsilon ji, which I again split as epsilon j wedge epsilon I. Now all that remains to be shown is that sine tau equals minus 1 raised to kl. So I won't do this. This can be perhaps discussed in the tutorial. It's just a matter of combinatorics. So one would like to write the permutation tau as a product of transpositions, and it will turn out that you need KL transpositions to do that. So essentially ij consists of I1 up to ik, j1 up to jl. This is ij, and ji will be j1, jl, I1, ik. So in order to move from ij to ji, I have to, or rather suppose I start from ji and I move to ij, I have to move this I1 past all this j1, j2, j1, j2 all the way up to jl, and I2. So first I do that, I move it all the way. So move it meaning that each time I can apply a transposition, I can interchange I1 and jl. So jl will come here, and then I interchange I1 and jl minus 1 and so on. So if keeping track of the number, one gets k times L number of transpositions. Now, so that completes our discussion. So let me just mention a couple of things which should not get lost in the whole process. So remark, we have proved I wrote that we have proved this, but I mean, we may not have explicitly stated it, but this is a thing which will be useful. If you start with, I've been using the notation omega 1 omega k as for the dual basis, but let's say one just starts with any k forms, k1 forms, and I evaluate it on any k vectors. Then it is equal to det omega I Vj is the what one would like to say. This is one thing, and the second thing is that this is something which has been explicitly proved. If T is a linear map, then and omega belongs to A and V, where n equals dimension of V, then T star, the pullback of omega, is determinant of T times omega. Now, I proved this in the case V is Rn, but exactly the same proof will work for any vector space. So you fix a basis and use the same basis for writing down for both the domain V and the target V. Write down the matrix of T in that and calculate the determinant, and one has this. So the same proof as in Rn will work for this. Now, as for the first one, that this equal to this can be proved by similar methods as what we have been employing so far. Namely, one wants to check this. The right hand side is also a multilinear map, multilinear form. We have seen this multilinear map in the context of when omega 1, omega 2, omega k are parts of a dual basis, but the fact that they came from a dual basis is irrelevant for the multilinearity. So one can define a multilinear map using any k1 forms in this fashion. And this, so in order to check that these two maps are the same, it's enough to take V1, V2, Vk to be basis vectors. Right. Oh, well, even before I come to that, in order to check that, so what we are claiming here, proof of 1, I'll just briefly outline it. So the right hand side is a multilinear map. Let alpha of V1 Vk be determinant of omega 1 V1 omega k V1 omega 1 Vk omega k Vk. Then alpha is a multilinear omega ak V. So one is interested in showing that alpha is equal to this. So what one wants is, let's use the basis that we have constructed of AKV and expand alpha in terms of the basis vectors. Actually, yeah, is it needed? No, maybe not. Yeah, well, the basis will, at this stage, it's not needed. So let's just evaluate it on, we know that this is alpha is multilinear, this is multilinear. So just evaluate it on any I1 as usual, EIK. It's enough to check this equal to omega 1 omega k EI1 EIK. Right. Well, when we plug in these basis vectors here, so here right. So when we plug in these basis vectors here, then these alpha of this, just going by definition, will give me determinant of omega 1 EI1 omega k EI1 omega 1 EIK omega k EIK. Now I'll use the dual basis. Unfortunately, I've already used omega for this arbitrary one forms. So the dual basis of EI, let eta 1 eta n be the dual basis of V star corresponding to E1 of V. So this omega 1 I can write as A11 eta 1 plus A1n eta n, and omega n an1 eta 1 plus ann eta n. When I evaluate omega 1 on EI1, I'll just pick up the AI1 coefficient. So this is determinant of A1 I1 A, and then this is AK I1, and here I'll get omega 1 IK omega k IK. Now on the right hand side, I can again plug in. So this is the left hand side. On the right hand side, I can again plug in this expressions for omega 1, omega 2, etc. Well, what one gets is First of all, one knows that a k r, let us say eta r, evaluated on, whole thing evaluated on ei1, eik. Now, in this expansion, again using multilinearity, lots of terms will come, but one notices that if the same index eta 1, for example, if eta 1 occurs twice, then this wedge product will be 0. And so basically with the same thing with any index. So essentially all the terms here will have to involve eta i's with different indices. And when there is the only things which will survive in the sum, so there will be one summation, I can bring the sum outside. The only terms which will survive are things with different etas with different indices, which is, then you will be evaluating on ei1, eik. So not only should they be different indices, that index set which will survive will have to be a permutation of this I1 up to Ik. And then the actual value will be just turn out to be just the sign of that permutation, which we have seen already. So essentially one is reducing this, the left hand side, to those basis forms that we had, and then we get this. So I won't go into details of this, but all the ingredients are there. But I will remark one thing, that this forms, hence this forms alpha is that I defined earlier, in terms of the determinant, because of this statement, because of this, the forms alpha as I defined earlier are just will be omega I1, omega IK. This is the main thing for us. So these things form a basis for what we have shown, and what we have used repeatedly in all the proofs is that these alpha i's, however, we did not know that this alpha I is actually equal to this wedge product. So here, oh sorry, not alpha I, this was what I've been calling epsilon I. It's epsilon I. Omega 1, omega n is a basis. So the remark I made here is for any one forms this equation holds, but what is more familiar and relevant is that if we start with a basis for one forms, here we just need k of these, but if we start with a full basis omega 1 up to omega n of V star, in that setting we had come up with this epsilon I k forms, which we called epsilon I, corresponding to any index set I. And with this remark, we see that this epsilon I is the same as omega I1, omega Ik. So this is something that I'll repeatedly use later on. And that pretty much concludes my discussion of constructions on finite dimensional vector spaces involving multilinear forms. Now let's return back to the setting of manifolds, and let's try to define these objects there. So tensors and let me just say tensors on manifolds. So what we need is on each tangent, so given a manifold at each point we have the tangent space, and we know that once we have a finite, we don't even need finite dimensionality. Once we have a vector space, we can talk about multilinear forms on that, which we call tensors. So when we given a manifold at each point, we have a, if we have a multilinear map, we call it a tensor on the manifold. And as usual, we would like to demand some kind of smoothness, that as you change from point to point, this multilinear map should change in a smooth way. And to quantify that smoothness, we'll use a trick which we had used when talking about smooth vector fields. We'll see its action on something which is already smooth, and then we want to, the net result should be smooth again. So let's say a K tensor on a manifold, a K tensor, let's say T on a manifold. No, T is not the good symbol. Let's K tensor alpha on a manifold M is an assignment. So I'm defining it exactly the way I defined a vector field. In a vector field, to each point I associated a tangent vector. Now I'm going to associate to each point in the manifold an element of LK TPM. For each P in M, I'll pick out in that particular tangent space a multilinear map. Right, and we require that this assignment is smooth in the following sense. Well, as I said, the idea is to act, so this is after all a map, a multilinear map, and so it's going to act on vectors and give me a number, but I can also, since there's a multilinear map at each point on the manifold, I can act it on K vector fields, smooth vector fields. Let x1, xk be smooth vector fields. Then the function p going to alpha p evaluated on x1 at p xk at p is smooth. So this is a function on the manifold. So if I define G from M to R, G of P is alpha P, x1P, xkp, i.e. if G is this, then G belongs to C infinity M. This is the requirement, and this should hold for any choice of vector fields x1 up to xk. Then we say that it's smooth. Then we say that this K tensor alpha is smooth. Well, and remember that in the case of vector fields, we had a more workable definition of smoothness in terms of local coordinates or charts. Here too, one can write this in terms of charts, and I'll come to that. Before I do that, let me if alpha p belongs to AP, no, AK TPM for all P, then we say that alpha is an alternating tensor on M, or alternating K tensor on M, or a differential K form on M. Unlike the vector space context, so now we add in this adjective, or just I mean it's not even an adjective. It's just for historical reasons. One says differential forms when talking about what would be just called an alternating K tensor, an alternating K form on a vector space is now called a differential K form on a manifold. As far as a tensor is concerned, you don't say differential, it's just say K tensor on the manifold. Now, right, so now that these objects are defined, I'll come to the coordinate description shortly, but before that, let's give it some names, these things. The set of K tensors and K forms. I'll not say differential, it's understood when I say K form, it's understood that it's a differential K form, in other words it's an alternating K tensor. Both these sets, the set of K tensors and K forms on M, form vector spaces over R. So we can add two K tensors just by adding them at every point, and likewise for K forms, denoted by let's use epsilon km and omega km respectively. The notation for the space of K tensors is not standard. Some texts use this, but this omega, capital Omega km for the space of forms is pretty standard. So I'll use this. and of course omega km is a subset of epsilon km. Alternating K tensors are just special kind of tensors. Alright, so we'll stop here. Next I want to talk about, these are just the objects. Then we have these operations, the tensor product and the wedge product. Both of them carry over to manifolds without any difficulties or subtleties. The additional element which was not there in a vector space will be this exterior differentiation operator on forms. So I'll talk about that in my subsequent lectures. Thank you.